Hey guys, let's go over the problem that's supposed to be similar to the one that is worth 40% of your grade in the exam. So this is question 2 on the 2012 AP Physics C Mechanics exam. It's an experiment type question. Basically, you want to prove conservation of energy more or less, and you got a bunch of the usual junk in a lab, and you want to set that up. Now, if you're going to show gravitational potential energy converting to kinetic energy, if you want to find gravitational potential energy, you are going to need a meter stick for sure. So guaranteed you need a meter stick. It'll also probably be useful for figuring out your velocity later on. You'll also need a stopwatch because there's no other way to figure out time or velocity. So it's the only option. Personally, I love a computer and PhotoGates, but we don't have that. All right, so the standard lab for this thing involves like a cart, a track, a string, a set of object of different masses, and a lightweight, low friction pulley, and the electronic balance. So it really looks like they're trying to set us up to do this like cart and pulley setup. So you got your lab table, your beautiful lab table. You get your cart, which you weigh. So you use your electronic balance to weigh it. You attach a string from it, goes to like your frictionless pulley, and then you weigh your known mass on it. And you take your stopwatch, you measure how far this guy goes, so the height it drops, and you measure how long it took. Using your little stopwatch. Beautiful stopwatch. All right, so that's kind of the gist of the lab. The reason you wouldn't usually just drop masses from a known height and time them is it's so quick and human reactions are kind of minimal. So let's say you're only accurate to about half a second. If it only takes a second to fall or less, then that's not good accuracy. But if it's taking like 10 seconds to fall, and you're accurate to within half a second, that's a much smaller percent of the total time, and so your error will be way less. So basically, if you were a computer or some hyper reflex person, just dropping the weights from a known height and measuring would be a great idea, but you're not. So we got to figure out some way to slow this process down, and this is one of the best ways to do it. Of course, it also adds friction, which will add other sorts of error. All right, so that's basically your procedure for performing the experiment. You'd want to label it, include a description of your measurements, and make a symbol for each measurement. So in this case, you need your mass of your cart. You would want know this mass. It would probably be labeled. It's called M2 or whatever. You'd have a height that the mass drops, and your time it takes to drop. And that's what you need to know. By the way, this guy will also move a distance h in the same time because they're tied together. All right. So let's talk about the calculations that we would use to figure out the gravitational potential energy before and after. So our gravitational, why don't we just do our before equals after? Before equals after. So before, we've got our potential energy. It's M2GH, measured with the bottom, the floor being zero height. and we'll assume it's at rest, like you hold everything and then you start the timer. And then afterwards, you're going to have a bunch of kinetic energy, which you will have to figure out the velocity. So why don't we figure out the velocity first, because we will need that in our before equals after. So our velocity will be h divided by the time we measure, except that would give us the average velocity. So our final velocity is just going to be our average times 2, because we started at 0. Alternatively, you can do the whole VAV equals VI plus VF over 2. And then if you rearrange that and VI happens to be 0, VF is just 2 times the average velocity. So you find your average velocity and then get your final velocity from that by doubling it, assuming you started at 0. If you didn't, you'd bust out this guy. And then once you have your velocity, you've got m plus m2, both moving at the same speed because they're tied together. And then we'd have 1/2 m plus m2. You'd probably call it m1. That's more traditional. V squared, V final squared. And so that's what that's how you'd set up your calculations. You would be assuming this to be true and taking measurements. So I guess really, for purposes of a lab and not purposes of perfect your calculations, you would say that this is your initial gravitational and this is your final kinetic. And if you've done things right, they should be pretty darn close. Really, this guy should be a little bit less because there's going to be some friction that you didn't account for, though you're probably going to have measurement error as well. Anyway, so that's the gist of C. For part D, your calculations show that the energy increased during the experiment. Assuming you made no mathematical errors, what could do this? Does energy come from nothing? Probably not. So you made an error somewhere. Now, the most obvious error is with this stopwatch. This guy here is totally error prone. So for part D, let's say the time was longer than you measured. So if the time was actually longer than you measured, if you hit the button before it actually hit the ground or something like that, or had some weird start, that would change your final velocity. That would increase it because you'd be dividing by a smaller number, which would also increase your final velocity, which would increase your final kinetic, which would say that your energy went up potentially. Other things that could screw it up is if you messed up measuring your cart, and let's say you measured your cart and your scale wasn't calibrated right, and it measured it as being heavier than it actually is. In that case, it would actually be lighter, and so this whole thing, you would calculate, you get the same velocity, you'd measure the right velocity, but this number would be bigger than it's supposed to be. And so that would give your final kinetic calculation, it would make it bigger than it's supposed to be. So the two ones that imagine, assuming these masses are weighed correctly, are your time was actually longer than you measured, or your mass was actually lighter than you measured. So on your other trials, your calculations show that the energy decreased during the experiment. Assuming you made no mathematical errors, give reasonable physical explanation for the fact the average energy you determined decreased. Now, there's friction in this. So that will just take away a bunch of the energy. You could also have the opposite errors in measurement that I mentioned before. You could measure your time as shorter than it actually was, or measure the mass as lighter than it actually was. So you could make a measurement error, or it could just be friction. You got friction in the wheels, you got friction in the pulley. That should make your final kinetic energy a little bit less than your initial. One other thing you could add, if this table isn't exactly level, that can also cause things. Anyway, thanks for listening. That's the question.